So hello everybody from ORI and everybody outside of ORI who has joined us together today. So to begin, of course, it's such a great pleasure to introduce Michiel Van de Panne today for our second ORI 5-year anniversary series seminar. To be completely honest, I feel that Michiel needs no introduction. I'd be really surprised if somebody here has not come across parts of the work of Michiel's research. He has published an incredible amount of highly influential work in computer graphics and in character animation. He has done work for human and animal characters. He has worked in robotics and more recently in DeepRL. And to name a few of the more recent works that I know for sure that many of us here have read through or at least skimmed through. So these are Deep Mimic, for example, and Deep Loco. Michiel has pioneered the use of physics-based models and controllers for avatar animation in computer graphics. And this was mostly in an effort to improve realism for rendered characters, so how characters move and interact with their environment, and of course to improve how also characters look. For example, how characters are skinned and how are rendered, or how textiles and hair is simulated. Michiel has won multiple very prestigious awards. He has won quite a few Best Paper Awards for SIGGRAPH, for MIG, which is motion in games, and iClear most recently. And these are some of the most prestigious venues in the field of computer graphics. So, in fact, I sincerely cannot remember seeing a SIGGRAPH highlight reel without Michiel's work in it, to be honest. So I've been introduced to Michiel's work fairly early, back in my student days. I remember, I think the first paper that I've come across was Symbicon, which stands for Simple Bipedal Locomotion Controller, which was, of course, a really interesting idea at that time. How you can compose controllers from simple control laws and arrive at a very robust overall controller for your system. And this also resonated a lot with me, coming from through research work like the one from the early quadrupedal locomotion work from the MIT of the CMU labs and so on. So I kind of feel like I'm standing between Michiel's talk now and you. So without further ado, let's all welcome Michiel. And Michiel, you can start.
Okay, great. Let me get started on things. Okay, just double checking. Can everyone see the screen? Is that good? If someone can confirm.
Yes, you're good to go.
Yes. Yeah. Okay, great. Thank you. Perfect. Thank you. Okay, great. Many thank you for the very kind introduction, and indeed for the invitation. It's a great pleasure to be here. And so this is all I'm building on the fantastic work of my students, and as I was just discussing with Ioannis, I literally all I seem to do is cheer my students on and to do great work. If you have questions at some point, I will not be directly monitoring the chat, but I'm happy to stop at any point in time and ask and answer questions, as well as my plan is to leave plenty of time for questions at the end. Okay, but so to begin with, perhaps the first thing you've noticed about the title is that it touches on both robotics and graphics, so realistic animated characters. And so let me talk briefly about that point. And so I'll begin by arguing that robotics, graphics, and biomechanics really share a long history. And so this began with the humble 4x4 homogeneous transformation matrices, which really are at the foundation of both, and both fields actually really began to build kinematic models using these at roughly the same time. Also, both fields very much interested in efficient physics-based simulations, and both efficient and accurate models of real-world phenomena. Also, interested in the modeling of skilled movement, and also in terms of tool sets. And so, in biomechanics, for example, trajectory optimization is very common, and as it is in graphics and via model predictive control in robotics. And so perhaps the major point that I'll touch on today is of commonality relates to how modern machine learning and reinforcement learning methods are being used by all these fields. And just by way of introduction, my first experience with robotics was, and this will date me, it actually comes back to 1986, where I worked with a small company in BC that at the World Expo in 1986 in Vancouver, they had an exhibit of two of these Excalibur robots that would fold paper airplanes and throw them into the audience. And so I remember many a late night trying to adjust the control paths for these robots and the calibration for these robots, because the main challenge was, as it would fold and throw autonomously these paper airplanes into the audience, the robots would slowly drift out of calibration, and so they simply lacked appropriate sensing capabilities. And so from that point on, I've always been interested in robotics. So let me walk you through. Let me give you a sketch of what I'll walk you through, which is the hype curve for is reinforcement learning a game changer for robotics, and if so, in what way, and how will this play out? So the classic hype cycle curve, from Wikipedia, is you have some technology and then a lot of inflated expectations that can come with it. Then you have reality that sinks in, and people have overestimated what the advantages of a certain tool are, and then we reach some trough of disillusionment. Then we at some point, with additional understanding of how a tool can be used, we reach the slope of enlightenment, and finally a more sound assessment of exactly how and when a tool can be used. So this applies to reinforcement learning as much as anything else. So let me briefly walk you through the parts of this curve. So this is probably a slide that needs not too much explanation, but so the reinforcement learning setting is as follows. So we have a actually, let me just do this 1 second. Okay, yeah, so we have a system that we'd like to control, and in some environments, and so we can model the state of both of these is modeled as some state S. We wish to learn some control policy pi, which maps from states to actions. This control policy will be parameterized by a neural network, which has parameters theta. And so we want to eventually produce, for example, control torques for a robot or a character. And given those control torques, the character will move through its environment and proceed on to the next state. And at the same time, we can model a reward which models how well our task, the task that we want to be solved, is actually being solved. And so so we wish to treat things as an optimization problem, perhaps over some fixed time horizon h, although this time horizon can be infinite in the case of a discounted reward, sum of discounted rewards for reinforcement learning, or it can be finite across some horizon h for model predictive control, for example. And so this is on paper, this is a fantastic method or a setup to just treat motion control as an optimization problem, right? Because to some extent we haven't excluded anything by setting up the problem in this way. So this is the problem setup, and now let's take a look at where this has taken us. So looking at results from a few years ago now, lots of progress in playing Atari, starting to generate interesting kinds of motions. And more recently, of course, AlphaGo, AlphaFold, and solving Rubik's Cube with the robot hand, etc. But I'd like to briefly dwell on when these first came out. Some of our own reflections was related to some of the challenges. So one of those is related to motion quality. So if you've done, for anyone who's done work in robotics, you look at these motions and you say, well, okay, this is interesting, but this is I would not run these particular control policies on my robot, nor is the strength of these characters particularly reflective of the strength of a real humanoid robot, for example. So now a second challenge is perhaps related to getting if you have your particular problem that you'd like to solve, how can you get this to work on your problem? And so what the previous introduction ignored was that there are many small decisions that you need to make to get this to work properly, and they all matter to some extent. So the structure of your policy network, the actual form of your state description, even something as simple as your control time step has an impact on the quality of the solution. What your reward function is, and does it offer sparse rewards or dense rewards? Does it contain regularization for the amount of energy you spend, et cetera? And so there can be quite a lot of details there. There's modeling problems related to the system that you want to control, and then there's all kinds of things related to the actual algorithm setup. And so arguably, the methods are potentially still slow and inefficient, difficult to author the rewards. There's no guarantee you'll find the best solution. So these methods are still prone to local minima, et cetera, and generally difficult to debug if you talk to anyone who's worked with these problems. So then one more point to mention is that of reproducibility. And so that this is just one paper that draws attention to the reproducibility issues, that in forever chasing better performance for learning curves, then there have been lots of challenges in terms of producing easily reproducible results that in particular that generalize well to other problems. Okay, so but having said that, let's say we still decide to use some form of reinforcement learning. Then what can we say about the solutions? Well, in general, the solutions that you learn for a policy, unlike model predictive control, the policy really ends up being very specific to the body that a robot that you're trying to optimize. So the kinematics and dynamics. It's specific to the environment you've trained for and the task you've trained for. And so in some sense, the solutions are not very general. However, the method itself is very general. And so the advantage of reinforcement learning is, of course, that we can deal with high dimensional sensory information, flexible objective functions, and flexible constraints. And so it's a win on that count. So having walked you through part of the hype curve, the good and the bad, let's take a brief walk on the moving towards the plateau of understanding what the methods can and cannot do. So here I'll quickly do a review of Deep Loco and Deep Mimic, which are two results that illustrate some of the potential of the reinforcement learning methods. And so in both of these, we introduce a motion imitation objective. And so here we are going to give ourselves some example motion that we wish to imitate. And so this can actually be a fairly crude kinematic sketch. It doesn't have to be motion capture data or something that's terribly accurate. It just needs to be a sketch of roughly what is the motion that we want to do. So that will be the imitation objective, simply some kind of a typically L2 distance between actual poses and desired poses. And then on top of this, we're going to add some kind of a task objective. So if we're doing a kick, we might want to kick towards a specific target. So what I'll briefly mention the method here, we're generally using policy gradient methods with some kind of a step size control. So PPO, proximal policy optimization. I will note as a footnote here that I do think that the field has become a little bit algorithm centric, whereas in practice, I think many of the issues related to that ultimately preclude these methods or from working, or that make them work really well, actually don't have that much to do with the actual algorithm, and so I actually but believe that we've become a little bit too algorithm centric. But I think one of the things that's a positive is to see to see interesting emergent behavior. And so here's this walking 3D simulated walking character. It's simply trying to imitate a very simple basic walk cycle, and at the same time it's trying to solve the task, and the task is really very simple. It's just trying to hit that first green dot you see. And so those two green dots represent the two upcoming steps. And so it's being trained to both imitate the some basic single reference motion clip, as well as trying to turn or take larger or smaller steps to hit that first green dot. So this already exhibits a fair degree of robustness simply from the training procedure. And so this is also often not quite appreciated, is that during training, of course, reinforcement learning is doing exploration, in this case by adding noise to the action space. And the same exploration, it consists of a type of self-perturbation, basically. And so that because it's seeing all these self-perturbations during training, it also tends to be fairly robust, produce a fairly robust policy that knows how to recover from these perturbations. And so what's interesting is you get these robust emergent behaviors, and which we can make it do various tasks as we see here. So then we can it's fairly easy to stylize, so we can change the constraints or the reference motion. Here we're locking both knees, and it's still learning how to walk. And so this would be to do this quickly with other kinds of methods could be fairly challenging. Whereas in the reinforcement learning setting, we're really free to play with objectives that add various style or other constraints to the system. So we extended this. So in terms of to more complex characters and more complex motions. And so here there's 197 dimensional states, and the policy needs to learn how to map that to a 36 dimensional action. In this case, the actions are not directly joint torques, but we happen to use for imitation-based tasks. It turns out to be more convenient to use target angles for proportional derivative controllers, or in this case, a target quaternions for each joint, and to use a proportional derivative controller. So if we optimize the humanoid motion just for forward motion, we can get something like this, which looks more like the early types of results that you saw. But now if we imitate motion capture data as seen on the right, we get a control policy as seen on the left. And so this you could argue, well, why are we doing this? Because we're just recreating the motion capture data. So of course, the control policy on the left, it can actually recover from a variety of situations. That's one reason. But it's also worthwhile pointing out that the motion on the left is actually in some sense better than the motion on the right, because motion capture data is, while it is a certain form of ground truth, it often needs to be cleaned up, and the feet will slip and also penetrate the ground, etc. So motion capture is not necessarily the perfect ground truth that we always like to think it is. These methods do hit local minima, and so here's an example. We're trying to imitate a backflip, and so this is a problem you have because it's easy for the character to fall, and then but it says, well, I've fallen already, but at least I can still win partial reward points to imitate the backflip while I'm actually lying on the ground, and so it gets stuck in this local minima. So we can by using early termination and reference state initialization, we can get out of these local minima. So we can we can penalize falling on the ground, or simply stop providing all rewards and stop the simulation when the character falls. So now it's hit a different local minima, because here it's no longer falling, and it's imitating the start of the backflip and the end of the backflip, and it's hoping that you don't notice that the actual flip part on the left is skipped. So we introduced this notion called reference state initialization, where we're going to begin episodes at various starting points, starting states on this backflip cycle. And so we're not going to run episodes just from the start of the backflip, but also from halfway through the backflip and 1/4 of the way through the backflip, etc. So when we do that, then indeed now we can get good backflipping motions. And by the way, there is also a curriculum that is used there. So you can begin with shorter episodes and then gradually extend these into longer duration episodes. So yeah, so this is maybe not too much unlike how if you or I had to learn a backflip, then you could imagine that being supported by some external device would let you get a good feel for what each individual segment of the backflip is like, and practice those bits first before finally putting them all together. And so so this is not an unexpected strategy. So we can add different types of sensory perception to this. And so here the character, again, its goal is simply not to fall down. And so so it realizes that it can use we can provide the policy with information on the upcoming terrain, and so it can learn to condition its actions on the upcoming terrain. And again, reinforcement learning is learning to do these small adaptations to this run cycle via exploratory noise that has been added. Of course, in the context of something that looks a little bit more like robotics, we can actually have a different kinematic system or dynamic system. So this is roughly modeled. This is modeled on the parameters of the Atlas robots, although we're giving ourselves liberty with a few points in terms of the strength of the actuators, and I believe here we also substituted additional. We did add some additional degrees of freedom to the robot here. But the point is, we really can begin to use motion capture data as a rich source of motions to learn from. Now, just to give you some sense of whether these stick figures, or these very crude figures that you're seeing here, can actually be used for visual effects and later robotics. Let me try to convince you of that. So this is a learned policy that there is no underlying motion capture data it's trying to imitate. Instead, there is a keyframed motion cycle, so created by an artist that provided a basic sketch of what a galloping lion might look like. And so then we collaborated with a local company in Vancouver, Ziva Dynamics. So they do physics-based muscle simulations, so finite element models, not to understand the forces that the muscles generate. So we're not going to use muscle-based forces. We're still going to use the joint torques, but to produce accurate models of the shape of the bulging muscles and sliding skin and that type of mechanics. And so when you put that together with the controller, we've learned this is exactly the same motion that you saw previously. only this is now rendered with a much more interesting model. And so now you can imagine that so this particular rendering was not produced in real time, but I now believe that that we could produce this kind of rendering in real time, and the underlying physics and control is in some sense runs trivially in real time. And so now we can have this lion that you can push and pull around, and it's can show intelligent behavior and respond to various things. And so this hopefully can give you some sense of the optimism that some of us have about the future of this kind of direction. Okay, so the lessons learned are you can really do fairly natural and robust imitation of many motions, and then add some task-driven variation on top of that, add perception on top of that, and you can also have policies that learn how to imitate multiple types of motions. And more recent work in this area actually conditions the policy on a short window of the future motion. And so it's really like it does some kind of inverse dynamics or predictive inverse dynamics of any of a large set of upcoming motions that you might want to imitate. And so this work pushed by others has gone well beyond just imitating single motion capture clips. And then yeah, I'll note that algorithmic novelty has maybe is good algorithms are important, but a lot of the details really needed to make this work tend to lie elsewhere. Briefly, we can add a high-level controller on top of this. So this high-level controller can look at the terrain and then it generates the target footsteps, which can then be used by the existing low-level controller that I already showed you.
For this task, the height map input feature is exchanged for a velocity map of the obstacles.
And so
after training, the high-level controller has learned to navigate to the target while avoiding moving obstacles.
All right, so hopefully you heard that audio. So it's getting a height field map of this moving obstacles and the high-level controller.
This soccer dribbling task, the high-level controller has learned to perform a sequence of subtasks in the correct order. It learns to first take possession of the ball, then to dribble the ball towards the target. Once the ball has reached the target, it learns to circle the ball while maintaining some distance to avoid perturbing the ball away from the target.
Okay, so yeah, there's just two reward terms here. One is character should be close to the ball, and the second one is the ball should be close to the target point. And so this with this high-level controller, it's working with a higher level of abstraction because it's sitting on top of this lower level controller. And this is an area where I think the field needs to see a lot more work is higher level abstractions of motion control. Okay, so let's get on to robotics. And so the question is, this is great. But for those of us that work with real robots, does it work on a real robot? And for the longest time, I would sit down with my other friends in robotics, and they would appropriately question me and saying, well, really, okay, you're doing all this work with game engines, but that's fantastic, but we work with real robots. And so please convince us that this will work on a real robot. And so I had fantastic conversations like this with Jonathan Hurst from Agility Robotics, and who was suitably skeptic at first, and to a certain extent I had my own doubts as well. But so here's the architecture that we're going to learn. So we're going to learn this control policy pi. We're still going to have some type of a reference motion, so some sketch of what the motion is a rough sketch of what the motion is that we want to get out. Instead of producing target angles, we're going to produce changes with respect to the reference motion. So these will be offsets from the reference motion, and we're going to use that to drive PD controllers for the joints. So by the way, if you do this, okay, so this is the first attempt. So we give it a reference motion, and in simulation, this all worked fine. And so we said, great, let's it looks like this is working. Let's see what happens. And so this is literally one of the first tests that we ran. And so this is what sim to real really looks like. the robot all set up, and this is Patrick Clary from Oregon State and Agility. And so, as you can see, okay, didn't work. And in fact, worse than that, during these early motions, the body really ended up shaking quite a bit, and so there were problems. So to get these fixed, there's a number of things you can do. Maybe most notably, one thing we did not do is what's called dynamics randomization. So dynamics randomization basically says, if I don't know the exact parameters of my physical system, what I'll do is I'll train on noisy versions of the physical system. So various masses, various coefficients of friction, etc. And then if my control policy is robust to those variations, then hopefully it will be robust to any mismatch between the simulation and reality. So we're actually not going to do that. But here are the other tricks that we use to help solve this problem. So we are going to for each we are going to add left-right symmetry. So for any given learning tuple, we also add and learn from the symmetric motion tuple. It's important to model the reflected inertia of the motors. So that's a very important component that we were missing at first. It's important to model delay in your control system from sensing to actuation. It's important to train using the state estimator that will actually be used on the robot instead of training with ground truth state estimates. So that made a big difference. And it also actually made a difference to train with the change in target angles as opposed to target angles. And then lastly, I'll note that our first basic template motion to imitate was simply stepping in place. And that turned out to be, in some respect, it's a poor choice, because if your policy has no memory, then each time a foot comes back down, the robot can't remember whether it should next lift its left foot or right foot, because it's in this perfectly symmetric state. And so that can confuse a policy that's only state conditioned. And so this is where we added phase to. We always still include phase as part of the as one of the inputs to the policy, and so that phase disambiguates the input. You could disambiguate this in other ways. So we could condition on we could apply the policy. We could give the policy some memory in some other way, or we could condition on a short history of the states in the past. Yeah, so I'll briefly comment that we can actually learn, we can train a policy with a large network and then distill it down to quite a small network. And so this policy you're seeing running on the real robot was literally only shown 600 samples and trained on a two-layer network with 60 neurons in each layer. And so when you do this distillation, you really can train a policy with surprisingly few samples and with surprisingly small networks. By the way, when you do this kind of training, then it's important to collect the right kinds of samples. So if you have a good working policy, then what we do is we collect samples from a stochastic version of the policy, and so that produces this kind of trajectory you're seeing here, and then so that makes us visit a variety of states, and not just states that are on the perfect limit cycle, and then for each state that we visit, we record the expert action of the not from the stochastic policy because that's always having noise added to it. But we record the deterministic expert action. So that's shown in green here. So it always wants to go back to the final limit cycle. And so these green arrows are effectively the actions that get recorded. But it is important to actually visit these states which deviate from the limit cycle. And so that will let you train on a suitable set of samples that not only lie on the expert trajectory, but also surrounding that expert trajectory. In any case, so here's a variety of other policies that have been trained, and so it's actually stepped off of the treadmill by accident, but no problem. It covers from that. There's going to be one other step off of the treadmill here, and this time it's too much. And I'm purposely showing you some of the failure cases because at some point when just seeing the motions that works, it gets boring after a while. But yeah, so we can train this to do forwards, backwards walks, sideways walks. So these are all just fairly small neural network policies. Here we're experimenting with different style objectives. So this style objective is asking it to lift the feet higher. The motion is being controlled with the joystick. So that joystick is basically specifying the desired, the goal speed and the goal direction. And so the policy is conditioned on wanting to go in a certain direction at a certain speed. And so, so this is this was actually we were just really happy with this test result. And again, so this is only being trained in simulation, no dynamics randomization, direct transfer to the robot, and it's really walking in a fairly robust way. Okay, so again, lessons learned. It's important to author the right objectives. So we did have to add regularization terms to remove unwanted accelerations of the body, and then there are various types of foot trajectories that are compatible with successful motion, and so but you want to provide some indication of what that should look like. And then for sim to real, there's a variety of points that are important to pay attention to, as I mentioned previously, and in this case, no dynamics randomization is used. So I want to briefly show this work, this continued work by Jonathan Hurst and other folks at Oregon State on. So you may have seen this. This is a blind biped stair traversal. So in simulation, it's actually seen a variety of steps walking up and down, but it's not given knowledge of those steps. It just knows that they exist, and it can learn about those steps via proprioception information, obviously, but it cannot. It doesn't actually have a vision system. And so what's surprising is just how robust you can make these motions. And just just via proprioceptive feedback and training on these in simulation, and again direct sim to real transfer, and so this was actually a really surprising result to me. Let me briefly also show some more work from Shubin Peng, who was the first author on Deep Loco and Deep Mimic. So he's done some really nice work on also imitating robotic locomotion skills by imitating an animal motion. So I call this real to sim to real. And so we can begin with a motion that you capture from a real dog, but of course the real dog has a policy. So we capture a single motion from that, we map it onto a character, then we retarget that to a quadruped. So this has a different number of degrees of freedom. So particularly the legs here only have 2 links, whereas the legs on a real dog, you know, depending on how you count, can have 3 or 4 links. And the spine in the real dog is much more flexible, whereas this is just a rigid body here. So we need to do some retargeting. Then we're going to use this kind of motion imitation task, like Deep Mimic, to learn a policy in simulation, and then we're going to transfer that back into the real world. And so here's what this looks like. And so I'm not showing you the original motion capture data, although this is that motion capture data mapped onto the dog. And so just to show you, it is possible to do this, real to simulation and back out to real, which I think is quite an interesting direction. So similarly, this also looks at the front end. In this case, not working with motion capture data, but with a computer vision system. So these are videos taken from YouTube of cartwheels and backflips, and then we can use these learned controllers as a regularizer to actually help us with the pose estimates for the reconstruction. And so, if we run a vision system on these individual poses, we might actually get quite noisy estimates of what the real pose is, particularly because you know, we're typically estimating 2D joint locations, and so it's not obvious what the full 3D pose actually is. But when you but it's okay if there's some noise in these estimates, because all we need for these controllers to work is that the poses should be somewhat consistent, and then you know, physics will do the rest to make sure that it's all consistent. And so yeah, so we can go directly from a video-based inputs to a controller, and then we can here's what this looks like for a backflip. And so yeah, I think once we can start leveraging, you know, videos from YouTube, I think that's a really exciting direction. And there is actually, so there is a mutual bootstrapping effect going on here, right? So here we're able to do better capture because we could learn policies, and in the future, you know, you can imagine we can learn better policies because we can do capture, right? So we could learn do better imitation learning. Okay, so physics-based imitation is a good regularizer, and there is this mutual bootstrapping going on. Okay, so maybe the last project I'll talk about before I move on to questions, and so this is one I'm really excited about. So solving stepping stone tasks, solving stepping stone locomotion using reinforcement learning. And so this is a video from a parkour group in the UK called Store Parkour, and so we had some email exchanges with them. We got permission to use some of their videos. I highly recommend watching what this group does. These are just amazing what they can do. The question is, okay, for robots and simulations, what can we do to be able to solve these kind of stepping stone tasks? And so we're going to set up a fairly simple reward function that the goal here is to make progress in forward progress, make contact. We're going to give it a target sequence of steps. So it has to step here, then it has to step here. We're going to give it an ordered sequence of steps. Generally encourage it to be upright, and a few other terms. But so here we are going to use torque-based control, and importantly, the policy only gets to look 2 steps ahead. So it's standing on the first step. It's standing on step 0. And it can see step 1 and step 2. All right, that's what it'll be conditioned on. So we're going to train this policy in a simulator, but this simulator is going to interact with a step generator. And what we're going to do is we're going to have a curriculum that begins with generating easy steps and then moves on to generating more difficult steps. And so maybe if you look in the top right here, this is the best way of illustrating this. And so it begins with the easy steps in the middle in some 2-dimensional parameterization of the space of possible steps. And then it moves to generating more difficult steps. And so that order turns out to be important. And I'll point to the paper for more details. But so yeah, so this is trained completely without motion capture data. So this is from a strict pure objective, if you want. And so if for some reason it's deciding to keep the hands just in more or less in front of the body, this is actually kind of a limit case where it gets stuck in this one step. This is kind of near the limit of what it can do in terms of trained steps up and steps down. And yeah, so this is pretty exciting because we're getting really fairly natural motions. Yeah, so there is control regularization on the output, so it is trying to minimize torques, etc. We can transfer this to Cassie, although we haven't done this with the real robots. But this is the same Mujoko model that's being used as we did previously for the transfer work with Cassie. Yeah, and we can map this to various kinds of terrains. We can do running or jogging. So this is moving more quickly. We can move to different types of characters, and we can tell it to stop and start. And so this is by playing with the goals. So interestingly enough, even for this small character, it is actually making use of the arms to maintain balance. And so in this next example, we've turned control. It's trained with the arms, but we've turned control of the arms off at test time here. And so now when we tell it to stop or tell it to move forward, basically it's falling because it can no longer use its arms. And so even though the arms aren't necessarily very heavy here, it is actually using its arms to maintain balance and help stop, etc. And this shows like we can continue the curriculum to generate leaps. And so we can imagine we're just gradually expanding the space of steps that can be tackled. And so I think curricula are really important for making progress on for difficult kinds of control problems. There's still a lot of limitations with what you're showing here. We've thought long and hard about how to extend this to quadrupeds, and we still haven't found exactly the right way, because for the biped, we're giving it an order in which to hit the different steps, whereas for quadrupeds, ideally we would want the individual legs to be free to choose which steps what stepping locations they step on next. And I'd be happy to talk more about this in questions. Briefly, I'll just show a result that shows that we can also learn learn something as difficult as a Fosbury flop. And so what you'll be seeing in the animation that I'll show you is the only bit of motion capture that you'll see is we use motion capture to train a run-up motion. But then the entire rest of the motion is actually trained using sparse rewards by jumping over a bar. And so it only knows whether it's successfully jumped over a bar. And we'll use a curriculum where we start with a very low bar, one that you can just almost step over, and then we gradually raise the height of the bar. And so by exploring the takeoff state, which is that last step, that last foot contact before takeoff, you can parameterize this in a low dimensional way, just according to various angles of the body and various angular momenta. So that's a low dimensional space you can sample from, and then from each of those samples, you can run a curriculum to produce a flop. And so as soon as it goes in the air, that's all learned motion, and so it's actually learned to do a Fosbury flop. And so we're really quite excited by this. This is what during the exploration process in reinforcement learning, this is what this looks like. And so you'll see that it knocks the bar off a fair bit. So this is near the peak, near the end of training, and so these are some of the stochastic variations you're seeing while it's still exploring. And then when you turn that exploration noise off, it can now do that successfully. And we can discover various different modes of going over the bar, and so that's kind of a limit testing case of what we can do. Current ongoing work, we're really interested in brachiation currently, and so this is just some of the most beautiful motion I've ever seen, and graceful motion of gibbons. And so these are just videos taken from YouTube. And so how can we achieve this kind of graceful motion? And so we're making some progress on this. And so this is actually just a three-dimensional action space with one action per swing. And so you get to control the swing time, the flight time, and a default length for the arm. So the arm will try to pull itself towards this default length, and that actually gives you most of the control authority that you need to be able to solve some fairly interesting and difficult brachiation problems. And so this is something we're really excited about. We're also actually building a solo 8 robot. So this is the one we've built on the left. So it's balancing using the IMU. And so where we want to go with this is shown on the right. And so we want to generate a variety of interesting motions that we can do with this particular robot, because it is very athletic. And so in fact, we've discovered that it can do a bipedal walk. So the nice thing is the joints can spin all the way around. And so we actually want to experiment with both bipedal and quadrupedal walks for this. So big picture, what's next? I think there is convergence, so at least some convergence happening between robotics, animation, and biomechanics. Arguably, this convergence was always there, because we're all interested in the same problem of controlling movement and skills. So I think we are fairly close to being able to see highly capable digital humans and animals that will populate various worlds, right? The NVIDIA Omniverse, the you know, who knows, Facebook Metaverse, etc. So these and the next version of Unreal and Unity. So they're already all equipped with physics-based simulators, and so the next step it really is to equip all these worlds with digital humans, and this includes car simulators, right, for simulating autonomous vehicles, etc. So we're getting close to being ready for that. I think we'll see a lot more between robot and control co-design. So at some point you really want to design the body together and mechanics together with the control that you know it's capable of, and now that we can come up with much more arbitrary control strategies, then I'm optimistic we could see a lot more diverse robot construction in terms of actuation and sensing. Yeah, and longer term, really, both model predictive control and model free reinforcement learning are really trying to solve the same optimization problem with different degrees of cost or compute amortization done in different ways, right? And so this is model predictive control. We're doing search, a lot of search and planning using the model, and here all the search and planning effort has been amortized into the policy. And so but they're really trying to solve the same problem, and so I'm really interested in deeper connections between these two, because as we know from methods such as AlphaGo, you actually do best when you do both of these at the same time. And lastly, yeah, temporal abstraction. We need to see a lot more work at higher levels of temporal abstraction, and so there's just so much left to do there. All this work was really done by an incredibly smart collection of colleagues and students and collaborators. So they've done all the hard work, and I'd love to stop here for questions and discussion. Thank you so much for your attention.
Thank you so much, Michiel. That was a fascinating talk. We have time for quite a few questions. So I can start with one as people start typing their questions in the chat. I have quite a few questions, to be honest, but I'll start with a sort of general one. Do you think we're constrained by the compute that we have access to for training these policies in RL, or if we should focus more on making the actual algorithm more efficient?
Oh yeah. I think you know, in the very short term, the biggest gains are just coming from doing lots of simulations in parallel on the GPU with Brax or RISIM or just I mean, RISIM is just CPU based, but it's a very fast simulator. So yeah, I think yeah, there's a lot to be said just for fast simulation. But at the same time, I do think yeah, you know, but personally, I try to avoid problems where just compute determines where avoid problems that are too dependent just on raw compute, because basically you know, the deep minds of the world and others will just do better than I can. They have access to far more compute resources, and they'll just kill me for if I try to compete directly with that. And so I do think there's yeah, you know, it's worthwhile aiming for problems where yeah, you have some specific insight or advance yeah, or strategic advantage. But yeah, in some ways there's no way getting around that compute still matters, unfortunately.
So let's take one from the audience. I can see Marco's question. He says it took several decades for humanity to discover the phosphor flop. Do you think the RL really discovered directly, or was the start of the motion being curved already suggesting to do that kind of jump? Did it apply the phosphor also for lower bars?
Oh yeah. You know, there could be, you could argue, you know, you always need to be aware of experimenter's bias, right? But there is no there. Yeah, so there is no direct. So it really did come up with the Fosbury flop, and it also comes up with these other solutions. And so like the only motion capture data that's in there really was just for the run-up motion, and then there was a Bayesian diversity sampling in a lower dimensional model of the takeoff state, and that takeoff state. So there is manual insight that went into this. So the prior information, you know, it's not complete magic. So there is prior knowledge that goes into the takeoff, into designing the shape, the low dimensional structure of the takeoff state. That's where the prior knowledge went in, basically knowing that, okay, the few things that matter are your approach angle to the bar. So at what angle should you run at the bar? And then at the takeoff state, you know, how far should you lead? What should your pitch angle be with respect to the bar? And with respect to your run, and then also the total angular momentum. So that's a fairly low dimensional parameterization. So so that's like a 4 or 5 dimensional space that we then sample from, and then within that space we run many optimizations, each one trying to go over the highest bar. And so we do see multiple of the high jump solutions, and in our case, I think the Fosbury flop is the one that does go the highest, although some of the other motions go almost as high. I'm not quite sure if the order of best to worst solution modes it exactly matches that of current athletic jumpers, but we did look at data on the torque limits for high jumps needed from the literature, and tried to match that to our character, because obviously those kinds of model parameters will also determine which jump style is the best, right? So yeah, good question.
All right, I can see Sam has his hand raised. I'll try to unmute him so he can ask his question.
Can you hear me?
We can hear you, yes.
Perfect. Great talk, Michel. I have a problem though. So basically, I think mocap is really cool because that's a way to generate motion that then you can train your policy on. But I think, correct me if I'm wrong, or I want to know your opinion. Somehow, to me, it seems a little bit limited. So the way that I'm thinking of it is that if you want to do a backflip, at least from a model-based perspective, controlling the ground reaction forces is really important, right? And so something like that you wouldn't get from mocap only, right? I think that's why, for example, the curriculum learning that you were talking about is a really cool way to start. But do you think, 2 questions here. One is, do you think when we're gathering reference motions, is it important to also try to find a way to get torques somehow, not just kinematics? And the second thing, apart from the curriculum learning and mocap, do you think what other ideas do you think would be cool to generate reference motions for the policy?
Okay, yeah, great. Oh yeah, so this is a great question. Yeah, I've often thought of, you know, what would the world look like if we had easy access to force cap instead of mocap, right? Because yeah, you know, obviously motion is driven by forces, and in fact, I've kind of been surprised by the fact that we haven't seen more work on automatically learning representations for control that directly model forces as the important latent variable, right? Because you know, we know that forces are the magic latent variable that determines how something moves. And so this is actually an interesting direction that I'd like to see more of. But so for the backflip, so basically you don't even need a very accurate backflip for motion capture, and so you could easily come up with some crude sketch of what that backflip looks like, and then and then the learning is trying to find a solution that doesn't stray too far from that actual motion, and it will learn to generate the appropriate forces, including the right ground reaction forces and takeoff forces to roughly follow that. So in some sense, that's convenient, because you're really, having a purely kinematic sketch is actually enough. That being said, I think I could also see imagining some kind of having an objective, like if you do have access to force plate data, then I could see also including that. Why not include in your motion sketch, just include both approximate forces and approximate sketch of the motion. And also you could learn a backflip without any mocap at all. So I think it would require a bit of careful thought, and like you would have to. I think you might need to come up with some kind of curriculum where at first you reward doing a quarter rotation, then you reward doing a half rotation, etc. So I think that there would be some kind of curriculum you could come up with for learning a backflip. The other way of doing this that people have looked at is actually to introduce assistive forces, right? So if you're learning to do a backflip in a gymnastics course or something, then typically you can have some kind of a harness, right? And so this is what you'll do on a trampoline. They'll put you in some kind of a harness, and where it's actually okay if you only make it halfway around, and so you can have the person who's providing an external assistive force, and so that's another way of having these kinds of curricula. But in general, I do think having curricula is an underexplored and underappreciated area. I mean, the curriculum for machine learning, I guess it was kind of popularized by the Bengio 2009 paper or something on using that for supervised learning. But I actually think the bigger application is for reinforcement learning. There is a counter argument for this, and so this is put forward by for example people working on quality diversity solutions. So Jeff Clune, also at UBC, he has these examples where you can show that if you have a particular point in the solution space, if you go on a direct line from A to B, that a curriculum won't get you there, and because it'll get stuck in some local minima. Whereas if you maintain a quality diversity solution, so if you maintain a larger number of solutions, even though they're not optimal for one task, but they're optimal for, they're each optimal for some task, but maybe not your current task, then you could always be mixing and matching those together, and that lets you go further than with just a straight curriculum. So yeah. But having said that, like I do think curricula get you go a long way, and I know because we had a trampoline in our backyard, and I was trying to and myself and my kids trying to learn how to do a flip, and so you can start by doing a roll, and a roll is already kind of like a flip, and then you do a roll with a bit of a jump, and etc. So there's a surprising number of cases where curricula really can work.
Cool. Yeah, I like the trampoline part.
Yeah, that was a
thank you.
A really comprehensive answer, yes. And also a side note, Jeff Bloom's keynote talk from Coral should be also available online now. This was very interesting a couple of weeks back. So Michael, if we can keep you for a couple more minutes, I have accidentally skipped one of the questions in the chat, one from Daniel. Would you think the internal dynamics of the reproduced motions are reliable enough, even across training seats, to be taken as approximations of the real-world dynamics, torque profiles, degrees of freedom, force distribution, etc.? Can we use them to make conclusions of the role of the degrees of freedom of the body, and to try to approximate the passive dynamics of the real bodies?
Yeah, let's see. Yeah, I do think looking at things like the actual torques generated by the policy is important. I always tell my students, I want to show me what they look like, and so there has been this, depending on what kind of your background is. Certainly from the machine learning side, if all you do is just stare at learning curves all day, you can just so easily be missing something really important about your system. And so yeah, and you see this with some control methods where if you actually look at what's going on, you can see this bang bang control behavior happening, and it's just hidden because people are just staring at the learning curves and the final motion. And then yeah, so instead of producing in between torques, I think there's a recent paper that kind of says, oh, bang bang control is all you need, but don't try to do this on your robot, right? So I do think it is important to look at these things. I think that yeah, I am interested in, or I think it's interesting to think about the actual control frequency that's needed. And so typically, we're seeing a lot of these simulations being controlled at 60 or 120 hertz. And so to me, that number seems high, because I think a lot can be done with, if you have some kind of impedance control of your actuator, like setting joint stiffnesses and just letting natural joint compliance deal with impacts and things like that. I think that needs to play a larger role. When I'm learning to do any kind of emotion, I am not making large changes in control at a rate of 60 hertz. There's just no way. And so I would argue that we need to be aiming for 10 hertz control. 10 or 15 hertz, I think you should be able to do a lot with that. And I think, I think with like for the animal, when you have series elastic actuation, that's providing a lot of that filtering for you, and that kind of impedance control. So that's useful. But I think we need to see more of that, and we need to see more people actually plotting, like show us what the actuation looks like over time. And yeah.
Good. All right. I mean, I would love to discuss with you about going from bipeds to quadrupeds and so on, but I'm afraid that this is going to be a really lengthy discussion. So instead, let's do one final question, kind of on a broader scale. A lot of work has gone into sim-to-real. Do you think at some point we'll be able to train on hardware?
Oh yeah. Let's see. I think I think we'll still be doing most of our training in simulation. So in practice, like the hardware, at least for the current methods, the hardware just isn't sufficiently robust to stand up to all that you would need, and even then, humans and animals don't train on the hardware. Animals are born and begin walking really soon, and that's because they're there's any number of arguments. One is that evolution has baked in the right kinds of basic control loops, and you're just fine tuning a few parameters. So and that kind of fits in with the meta learning perspective, right? Saying you're really only tuning a few things. And then you could argue there's a curriculum there because it's based on you're not going to start. You're going to learn by just first learning to maintain balance, and then move on to the more difficult motions. So there's curriculum there. There's a curriculum in terms of body size over time. So yeah, I don't think doing raw training on hardware. Honestly, I just don't think it'll ever really make sense.
Yeah. Okay. Michiel, thank you so much. I'm sure you have a busy day ahead of you. And everybody, I guess, on behalf of everybody, thank you so much, Michiel, once more. And have a wonderful day. Yeah,
it was a pleasure. Yeah, and many thanks to everyone for all the great questions. And this was really fun. I happy to also answer questions by email if people have follow-up questions.
Great.
Cheers.
Thanks so much.
Thank you so much. Bye-bye.
Bye.